In this lesson, we shall focus on rates of chemical reactions. But to start with, we answer the most basic of questions in terms of what is a reaction rate. Right, we note that in a chemical reaction, the substances that actually are undergoing the reaction are called the reactants, while the substances that form as a result of the reaction are called the products. Now, the reaction describes how quickly or slowly the reaction takes place. In other words, this reaction rate describes how quickly or slowly the reaction takes place. So how do we know whether a reaction is slow or fast? One way of thinking, or one way of knowing, is to look either at how quickly the reactants are used during the reaction, or at how quickly, right, the products form. For example, iron and sulfur react according to the following equation. Right, so let's look at the chemical reaction, right, between iron as a solid and sulfur as a solid. And we're able to see that we have obviously the iron sulfide. Now, in this reaction, we can observe the speed of the reaction by measuring how long it takes before there is no iron or sulfur left in the reaction vessel. Right, so to analyze that, we take a look at what happens, for example, when we have our iron as a solid, there's iron, and there's sulfur as well, it's a solid, and we're able to see the product formed. And here is iron sulfide that is formed. And we are then interested in understanding a couple of things, but I want us to, okay, I'm going to bring a tool here. Right, I'm going to bring a tool. I'm going to bring another cursor that we're going to use. I'm going to bring another cursor that we're going to use. I'm going to bring the pen cursor. Okay. So in this reaction, obviously, first things first, we can observe the speed of the reaction by measuring how long it takes before there is no iron or sulfur left in the reaction vessel. Okay. So we note that we can observe the speed of the reaction. How do you observe the speed of the reaction? We observe the speed by measuring how long it takes before there is no iron or sulfur left in the reaction vessel. In other words, the reactants have been used. So yeah, we are dealing with how long it takes before all the reactants are used up, and we do not have any reactants left. We do not have any iron, nor any sulfur, but we have just iron sulfide as a solid in the reaction vessel. In other words, the reactants have been used. Alternatively, one could see how quickly the iron sulfide, which is the product, forms. Alternatively, instead of looking at the reactants and how quickly they are used up, we can say alternatively, one could see how quickly the iron sulfide, which is the product, forms. How quickly does iron sulfide form? Okay, so we're looking at two ways. Either we focus on the reactants and say how quickly do they get used up, and then we're left with nothing in terms of the reactants. But also we can say how quickly the iron sulfide forms, and in other words, how quickly the product forms. Now, since iron sulfide looks very different from either of its reactants, this is easy to do. Okay, so yeah, a couple of things now. So we really are saying, since iron sulfide looks very different from either of its reactants. Okay, now if you look very carefully, here is iron, and look at its color and its appearance. You look at sulfur and its color and its appearance. Now you look at iron sulfide and the fact that it looks really very different from the iron, which is a solid, and the sulfur, which is a solid there. So yeah. Right, since iron looks very different from either of its reactants, this is easy to do. Okay, so yeah, it is easy to do because it looks very different, and then we're able to see that, okay, now in this reaction vessel where we've put together the iron and the sulfur, there's just no iron left, no sulfur left. There is only iron sulfide. And since the iron sulfide is different in appearance, you can quickly see, okay, what I'm seeing now in this reaction vessel, there's just no iron, no sulfur. It's just iron sulfide, meaning that the reactants would have been used up. And obviously, we say, how long would that take? Okay, let's look at in this example. Right. So in another example, let's look at this very, very famous example. And in this example, we're looking at the reaction between magnesium, which is a solid, and oxygen gas. And we then form magnesium oxide, which is a solid. In this case, the reaction rate depends on the speed at which the reactants of oxygen, gas, and solid magnesium are used, or the speed at which the product, which is magnesium oxide, is formed. Okay, this is very, very important. So in this chemical reaction, when we are reacting magnesium as a solid and also oxygen as a gas, we are looking at two important things. But what are the important things that we consider here? Let us look at these together very, very carefully. Right, we'll look at these very carefully. So we are really saying, okay, we're putting together magnesium, a solid, oxygen, a gas, magnesium oxide is the product. In this case, the reaction rate depends on the speed. So what does the reaction rate depend on? The reaction rate depends on the speed at which the reactants, which are namely oxygen gas and solid magnesium, are used, or the speed at which a product, which is magnesium oxide, is formed. So the reaction rate depends on two things. What is the first thing that the reaction rate depends on? It depends on the speed at which the reactants are used, or the speed at which the product is formed. So the rate is about speed. It's about speed. The reaction rate is about speed. What speed are we talking about here? So there are two speeds we're speaking about because we're having either reactants or products. So the speed, right, at which the reactants are used, or the speed at which the product, which is magnesium oxide, is formed. Two things: products, reactants, and reaction rate depends on the speed at which the reactants are used, or the speed at which the product is formed. Now, that's part of our learning of the reaction rates. We are going quite back to the basics, and we're trying to build this section from scratch. Now, the couple of things that are at the center of operations, but something very key is the notion of what we call the reaction rate, the definition as a fundamental concept. And let's look at the definition, as you'll be looking at the past exams and you'll be expected to know how to define. Okay, right. At this point, what do we mean by reaction rate? Let's define that together. So reaction rate means the average rate of a reaction. Describes how quickly reactants are used or how quickly products are formed during a chemical reaction. We repeat. So we're defining reaction rate. So the average rate of reaction describes how quickly the reactants are used or how quickly the products are formed during a chemical reaction. Okay, let us look at the average rate of a reaction. So the average rate of reaction is expressed as the number of moles of reactant used divided by the total reaction time. Okay, so how do we express average rate of a reaction? The average rate of reaction is expressed as the number of moles of reactant used, divided by the total reaction time, or the number of moles of product formed divided by the total reaction time. Okay, so these are the kinds of things that are very important. Okay, I want us to continue, but also analyze this concept together. Okay. Now, we looked at the average rate of a reaction and the fact that it describes how quickly reactants are used or how quickly products are formed during a chemical reaction. Now, the average reaction rate for the use of a reactant or the formation of a product, because we're looking at the reactants versus the products. Right, so now the use of a reactant means that the moles of reactant used divided by reaction time, formation of a product. The moles of product formed divided by reaction time. So, okay, well, look at these two formulas that we use that we can use. And in particular, we use them, but obviously we have the potential to choose in terms of which one to use here. So the average reaction rate for the use of a reactant, which means we are dealing with the moles of reactant used, or the reaction time in seconds. Or we decide, okay, we don't want to look at the use of a reactant. We want to look at the notion of a product, formation of a product. So we look at the moles product formed divided by the reaction time. All right. What is all this here? And what do we make of these ourselves? We introspect, but very cautiously, right? Using the magnesium reaction shown earlier. Now, let's look at the notion of the magnesium reaction shown earlier. Let's use that one. So we saw obviously in that case that we had magnesium, 2 moles of magnesium solid, plus 1 mole of oxygen gas, and that gave us 2 moles of magnesium oxide as a solid. Okay. Using the magnesium reaction shown earlier, the average reaction rate of magnesium being used. So we saw that in that reaction of magnesium and oxygen, the moles of magnesium used divided by reaction time, or the average reaction rate. Okay, so in other words, we're looking at the average reaction rate of magnesium being used. So that one is moles of magnesium used divided by reaction time in seconds. And we have the average reaction rate of oxygen being used. So we look at each reactant, because there are 2 of the reactants, magnesium and oxygen. And then now we looked at the magnesium being used, which is moles of magnesium used, and the average reaction rate of oxygen being used, which is moles of oxygen used divided by the reaction time in seconds. Okay, so we continue to analyze this, but very, very carefully. So yeah, we look at each reactant separately. Okay, we are still looking at the rate and extent of reaction. Alternatively, instead of looking at the reactants, which are namely magnesium and oxygen, we can look at what we call the average reaction rate of the product, which is the average reaction rate of magnesium oxide being formed, which equals the moles of magnesium oxide formed divided by the reaction time in seconds. Yeah, so we can look at the product that is being formed. And now to look at to calculate the average reaction rate of magnesium oxide being formed, we look at the moles of magnesium oxide formed divided by the reaction time in seconds. Okay, let's look at an example here. How do we study these things, and what kind of an example can we sort of be in a position to sort of give here? Let us look at these together. So at this point, we're able to look at a specific example that is of essence to us. Example 1 is about the notion of the reaction rates. Right, example 1 is on reaction rates. And here's the question. The following reaction takes place, and we have lithium as a solid plus oxygen gas. And this gives us 2 moles of lithium oxide. And now we then say, right, after 2 minutes, 4 grams of lithium has been used. Okay, here is lithium, and lithium reacts with oxygen, and lithium oxide is formed. After 2 minutes, 4 grams of lithium has been used. Calculate the rate of the reaction. Okay, now we're looking at the rate of the reaction in this example. And now after this, we shall be, continuing to look at past examination questions on this note. But now we're then saying in step 1, how to calculate the number of moles. Okay, yeah. First, we want to find the rate of reaction. And this example, we've done it so that we can just discuss exactly step by step what exactly happens here. But also, we can look at how you need to answer your questions in the final exam, given that this topic itself is very, very examinable. So let us look at first things first. How do we calculate the rate of the reaction, given that 4 grams of lithium has been used? So yeah, one of the reactants has been spoken about and has been quantified as 4 grams of lithium that has been used. Right, so it's after 2 minutes of time. Okay, step 1, for us to calculate the rate of the reaction for this one, let us see what we do. First things first, we're going to calculate the number of moles of lithium that are used in the reaction. So we're going to calculate the number of moles of lithium that are used. Right, so because we're given the mass of lithium, so the number of moles is mass over molar mass. So in other words, now we actually look at the fact we have the 4 grams, which is the mass of lithium, and we divide that by the following. We divide that by the molar mass. Okay, so yeah, so the mass is 4 grams. The molar mass from the periodic table of lithium is 6.94 grams per mole from the periodic table of the elements. And if we divide 4 by 6.94 using a calculator, we get 0.58 moles. Okay, good. Now this is what we have. Step 2, calculate the time in seconds for the reaction. Calculate the time in seconds for the reaction. Right, so to calculate the time in seconds for the reaction, we do the following. Okay, now let's continue with that part. Right, so because we want to calculate the rate of the reaction, we found the number of moles of the reactant, and then now we want to calculate the time, and the time is after 2 minutes. So 2 minutes can be converted to seconds because we say 2 times 1 minute is 60 seconds, and 2 times 60 is 120 seconds. Okay, good. Okay, so step 1 was to calculate the number of moles. That was step 1. But step 2, we calculate the time in seconds for the reaction. In step 3, we calculate the rate of the reaction. How do we then calculate the rate of the reaction? Right now, the rate of reaction of lithium used is the moles of lithium used divided by the time taken. So to calculate the rate of the reaction is the moles of lithium used divided by the time. So the moles of lithium used, we have already got the moles, 0.58 moles, and the time is 120 seconds. And therefore, this is 0.005 moles per second. Okay, and this is the reaction or the rate of reaction of lithium used, and therefore the rate of the reaction is 0.005 moles per second. Okay, so yeah, it's an example where we used we were able to calculate the rate of the reaction there when we're given the mass of the when we're given the mass of the of lithium that had been used there. Okay, but now let us continue to to crack more science. Okay, now let's look at the next point. Let's look at the next point. Now, there are things we call reaction rate and collision theory. Reaction rates and collision theory. Reaction rates and collision theory. Okay, now let us speak about the collision theory here, because it is very important in the exam, but also it's something you need to know and understand. Right, it should be clear now that the average rate of a reaction varies depending on a number of factors. So the average rate of reaction varies depending on the number of factors. But how can we explain why reactions take place at different speeds under different conditions? So we want to explain why reactions take place at different speeds under different conditions. These reactions occur at different speeds under different conditions. But why are the speeds different under those different conditions? And we examine this, but we examine this very cautiously. Now, for a reaction, for example, for a reaction to occur, the particles are reacting, or the particles that are reacting must collide with one another. Okay, for a reaction to occur, the particles that are reacting must collide with one another. Only a fraction of all the collisions that take place actually cause a chemical, what you call a chemical change. So, okay, now let us look at these, but yeah, understand these very, very well. So we are really saying, right, for a reaction to occur, the particles that are reacting must collide with one another. So for a reaction to occur, the particles that are reacting have to collide with one another. There have to be collisions for a reaction to occur. But only a fraction of all the collisions that take place actually cause a chemical change. So in other words, you have a fraction of all collisions that take place cause a chemical change. So there are some collisions that do not cause a chemical change. There are some collisions, therefore, that do not cause a chemical change. These are called successful or effective collisions. So yeah, the successful or effective collisions mean reflect the fact that you have chemical change that's happening because of those collisions, and therefore those collisions that cause chemical change are called effective collisions. And obviously, there are those that are called successful collisions, and the successful collisions are those that cause chemical change. So we then continue. Okay, let us give a definition. The next definition is, what is collision theory? What is collision theory? I mean, what is the meaning of collision theory? Reactant particles must collide with the correct energy. Right. Okay, we'll continue. All right, collision theory. Reactant particles must collide with the correct energy and orientation for the reactants to change into products. So there are a couple of factors that we look at here. So these reactant particles must collide with the correct energy and orientation for the reactants to change into products. So you need correct energy. There has to be a collision. The particles must collide with correct energy and orientation for the reactants to change into products. They need to collide with correct energy and orientation for the reactants to change into products. Because if they do not, if the collision does not occur with correct energy and orientation, then the reactants are not going to change into products. So you're not going to be having the kind of successful or effective collisions that cause chemical change. Okay. Right. So yeah, these are the things we need to sort of understand the basics. But I want us to look at the notion of what we call the collision. Now, collision theory explains how chemical reactions occur and why reaction rates differ for different reactions. So collision theory explains how chemical reactions occur. So to explain how chemical reactions occur, we bring what you call collision theory and why reaction rates differ for different reactions. Right. It states that for a reaction to occur, the reactant particles must collide, have enough energy, have the right orientation at the moment of impact. So yeah, there are three things that collision theory embodies. What does it embody? So it states, so collision theory states that for a reaction to occur, the reactant particles must collide, they must have enough energy, and they must have the right orientation at the moment of impact. These successful collisions, or what we call effective collisions, are necessary to break the existing bonds in the reactants and form new bonds in the products. So we need these effective collisions or the successive collisions, and these are necessary to break the existing bonds in the reactants and form new bonds in the products. We continue. We continue. Right, so right, let us look at the factors that affect factors affecting reaction rates. There are certain factors that affect reaction rates, and you are saying several factors affect average rate of, or affect the average rate of a reaction. So okay, we continue. Right, we continue. There are factors affecting reaction rates. Several factors affect the average rate of reaction. It is important to know these factors so that reaction rates can be controlled. It is important to know these factors so that reaction rates can be controlled. This is particularly important when it comes to individual reactions. This is particularly important when it comes to individual reactions. Right. Right. We'll continue. Okay, we continue. So nature of reactants. Okay, this is particularly important. Let's start there. This is particularly important when it comes to, industrial reactions. Industrial reactions where greater productivity leads to greater profits for companies. The following are some of the factors that affect the average rate of a reaction. Nature of reactants. Substances have different chemical properties, therefore react differently at different rates, e.g. the rusting of iron versus the tarnishing of silver. Yeah, so the nature of reactants becomes very important. So as factors that affect reaction rates, we look at the nature of the reactants. It's a factor that affects reaction rates, the nature of the reactants. Substances have different chemical properties and therefore react differently because of the different chemical properties and at different rates. For example, e.g., the rusting of iron versus the tarnishing of silver. Okay, we continue. So we looked at the nature of reactants as a factor that affect reaction rates. And let us mention some of these in passing. Let us mention some of these in passing. Okay, the nature of the reactants, and obviously an experiment can be done to determine the effect of the nature of reactants on the average rate of a reaction. Right, so you can always do an experiment. But we want to discuss the theoretical aspect of it, but also the notion of what you call the surface area. The surface area of solid reactants. Okay, so the surface area obviously applies to mostly solids, because that is when we are able to increase the surface area or sort of reduce the surface area. Okay, so surface area itself, in view of what you call solid reactants, an experiment is done, for instance, where surface area and reaction rate are being given attention. But marble, which is calcium carbonate, reacts with hydrochloric acid, HCl, to form what you call calcium chloride, water, and carbon dioxide gas, according to the following reaction. Let us look at the reaction between marble with HCl. Right, so at this point, we understand a couple of things. That marble itself reacts with HCl, and when it reacts with HCl, it forms three products. What are the three products when marble reacts with HCl? So it forms calcium carbonate. It forms calcium carbonate and HCl forms calcium chloride, water, and carbon dioxide gas. Okay, just look at that chemical reaction there that we need to sort of understand very well. Right, so I want us to look carefully at this. So in this particular experiment, we want to determine the effect of the surface area of reactants on the average rate of the reaction. Surface area, the effect of surface area of reactants on the average rate of the reaction. To say that the surface area of the reactants affect the reaction rate of the reaction or not. So this is what we consider, right? We take this into account. That's what we want to determine. But we're noting that I want to just say that we want to look at the effect of surface area when you look at the solid reactants. In other words, when you take marble, does it make a difference when the marble is one large block, one large solid, one large brick, if you like, or if it is subdivided into smaller particles? So in other words, the marble, calcium carbonate, reacts with hydrochloric acid, HCl, to form calcium chloride. So it reacts with hydrochloric acid to form calcium chloride, which is CaCl2, water, and CaCl2 is a solid, water a liquid, and the carbon dioxide gas, indeed a gas. Okay, so we continue. We continue. Right, so in continuing, there are a couple of things that remain very, very important here. Right, there are very important things that we need to take into account, and we hereby do. Surface area we have seen. Right, so not going to waste a lot of time, but yeah, just need to mention some of this. But also for solutions, we note concentration. Concentration becomes very important, and we mention concentration when it comes to solutions. And now, as the concentration of the reactants increases, so does the reaction rate. Okay. So as the concentration of the reactants increases, so does the reaction rate. So yeah, when we increase the concentration of the reactants, we anticipate the reaction rate to also increase. In other words, in this experiment, the concentration and reaction rate obviously work together. So determine the effect of reactant concentration on reaction rate. Okay, so yeah, and obviously we can use in this experiment concentrated hydrochloric acid HCl, the magnesium ribbon as well. So we're using HCl with magnesium ribbon as a solid, and two beakers, two test tubes, and a measuring cylinder. Yeah. So, but now at this point, I want you. The aim is not to look at the experiment, but is to really say, concentration itself. Want to look at how these questions are asked and to discuss how we answer questions in the exam. Right. So as the concentration of the reactants increases, so does the reaction rate. Now, and obviously at this point, we combine, for instance, concentrated HCl in magnesium. So if you take magnesium ribbon and you put it in concentrated hydrochloric acid. So as the concentration of the reactants increases, so if you take HCl that is a higher concentration, and HCl that is a low concentration, but you take HCl that is a higher concentration, you put magnesium in it, magnesium ribbon in it, low concentration, high concentration, but in both test tubes, you put magnesium ribbon, what happens? Okay, so yeah, we understand that as the concentration of the reactants increases, so does the reaction rate. Right, so yeah, the couple of things that I want us to discuss. Okay, now this what we call pressure. Pressure. Okay, let's discuss pressure here. Let us discuss pressure here. Let us discuss pressure here. Okay, now the notion of pressure of gaseous reactants. Gaseous reactants. And now pressure itself as a factor. So as the pressure of the reactants increase, so does the reaction rate. As the pressure of the reactants increase, so does the reaction rate. So the higher the pressure, the more particles of gas per unit volume. The higher the pressure, the more particles of gas per unit volume. Therefore, there are more collisions per unit time. The number of successful collisions per unit time will be higher, and so the rate of the reaction will be faster. Okay, let's discuss pressure in the case of gaseous reactants. So we're saying as the pressure of the reactants increase, so does the reaction rate. As the pressure of the reactants increase, so does the reaction rate. In the case of gaseous reactants. So the higher the pressure, the more particles of gas per unit volume. If the pressure is high, a higher pressure means more particles of gas per unit volume. A higher pressure means more particles of gas per unit volume. So we continue. We continue. We continue. We continue. Right, so we continue. We continue. Right, as the pressure of the reactants increase, so does the reaction rate. So does the reaction rate. Okay. Okay, let's continue. So the higher the pressure, the more particles of gas per unit volume. Therefore, there are more collisions per unit time. Therefore, there are more collisions per unit time because the more particles of gas per unit volume at higher pressure. Therefore, there are more collisions per unit time. The number of successful collisions per unit time will be higher, and so the rate of the reaction will be faster. Will be much, much faster. So we continue. Now, temperature. Temperature is one factor that affects reaction rates. Temperature is one factor that affects reaction rates. If the temperature of the reaction increases, so does the average rate of the reaction. If the temperature of the reaction increases, so does the average rate of the reaction. So yeah, the average rate of the reaction appears to increase with increasing temperature, but obviously, I mean, we know the kinds of different types of reactions like your exothermic and yeah, endothermic and so on, and we shall take that into account. But we're looking at temperature as a factor that affects reaction rates. Right. So yeah. So we continue. And obviously, I mean, there's an experiment that can be done where the aim is to determine the effect of temperature on reaction rate. And now we want to know. So yeah, when doing an experiment, we want to investigate. And the aim of this is to determine the effect of temperature on reaction rate. So if we increase the temperature, what happens to reaction rate? If we decrease the temperature, what happens to reaction rate? And that is what we investigate. The apparatus means 2 effervescent tablets, an ice bath, 2 test tubes, 2 balloons, which are 2 rubber bands. Okay, so have that kind of an experiment. I'm not really going to spend time on that, but also the idea of what they call a catalyst. Catalyst. Okay, let's look at the notion of a catalyst. So now a catalyst. Adding a catalyst increases the reaction rate by lowering the energy required for a successful reaction to take place. So adding a catalyst increases the reaction rate. So if you add a catalyst, we expect that it will increase the reaction rate by lowering the energy required for a successful reaction to take place. So it lowers the energy required. A catalyst speeds up a reaction and is released at the end of the reaction completely unchanged. So yeah, a catalyst itself is not a reactant. So, and this is very important. So it's saying adding a catalyst, what does it do? Adding a catalyst increases the reaction rate. Increases the reaction rate by lowering the energy required for a successful reaction to take place. So how does a catalyst increase the reaction rate? So a catalyst increases the reaction rate by lowering the energy required for a successful reaction to take place. By lowering the energy required for a successful reaction to take place. So we continue. We continue. A catalyst speeds up a reaction and is released at the end of the reaction completely unchanged. Okay, as an experiment, for example, one can look at catalysts and reaction rate, and the aim being, for instance, hydrogen peroxide decomposes slowly over time into water and oxygen. The aim of this experiment is to determine the effect a catalyst has on a reaction rate. So yeah, I'm going to use a couple of things like your apparatus, Your apparatus would be, for instance, 3% hydrogen peroxide and manganese dioxide, MnO2, and you have which is powder, solid, yeast powder, and 2 beakers or large measuring cylinders. So these are the things these are the apparatus that you're going to use here. Those are the apparatus you're going to use here. Those are the apparatus you're going to use here. Okay, we continue. We continue. Okay, so yeah, catalysts and reaction rates. Okay, yeah, we're going to look at a couple of experiments that we can use. Okay. I want us to obviously continue and look at potentially more. Okay, let us look at this example. Here's an example. In this example, we're going to say, here's a worked example 2. We looked at the first example. We're looking at the second example. So we're calculating the average reaction rate in the first example, but now we're looking at reaction rates in example 2. Write a balanced equation for the exothermic reaction between zinc solid and the HCl, which is the hydrochloric acid as a liquid. Also name 3 ways to increase the rate of this reaction. 3 ways to increase the rate of this reaction. Three ways to increase the rate of this reaction. So yeah, write a balanced equation for the exothermic reaction between zinc solid and HCl. Write a balanced equation for the exothermic reaction between zinc solid and HCl. Also name 3 ways to increase the rate of this reaction. Okay, yeah, here is the question, is an example. Let's discuss the solutions. Right, in the first step, we want to write the equation for zinc and hydrochloric acid there. And the products must be a salt and hydrogen gas. Zinc ions have a charge of 2+, while chloride ions they have a charge of 1-. Therefore, the salt must be zinc chloride. So you have that zinc solid plus a HCl in aqueous state will actually, as a consequence, form zinc chloride and hydrogen gas. So we are looking at the fact that if you react, okay, yeah, you react zinc as a solid, and you put the solid into the aqueous HCl, hydrochloric acid, you have zinc chloride and the hydrogen gas. Step 2. Okay, we've already written, this is the parametric equation. You have 1 zinc, and you have 1 zinc here, and you have 1 hydrogen. You have 2 hydrogen, so it's not balanced. And obviously, you can see you have Cl2, so you have like 2 chlorines here. You have a single chlorine here. So yeah, this is not balanced. Yeah, write the equation for the zinc and hydrochloric acid. This is the equation. So yeah, zinc chloride and hydrogen gas. Let's balance the equation if necessary. There are more chloride ions and hydrogen atoms on the right. So there are more chloride ions. We have more chloride ions and hydrogen atoms on the right side of the equation. There must be, therefore, there must be like 2 HCl on the left. So yeah, you can just put a 2 there. So that if you put a 2 there on the left side of the equation, right, so that we have 2 hydrogen and 2 hydrogen here, hydrogen atoms, and you have Cl2, and you have to chlorine chloride ions as well there. Okay, so you really can see therefore that this is certainly a balanced chemical equation. Okay, step 3, think about the methods mentioned in this section that would increase the reaction rate. Think about the methods mentioned in this section that would increase the reaction rate. A catalyst could be added. So, yeah, think about the methods mentioned in this section. Or, yeah, the factors that affect the rate of a reaction. So think about the methods used in this section that would increase reaction rate. Like a catalyst could be added. Okay, so if we decide to add a catalyst, and we expect that to increase the reaction rate, or the zinc solid could be ground into fine powder, because you have zinc, which is a solid. You can increase the state of division, you can increase the surface area. How to increase the surface area? So at this point, to increase the zinc solid could be ground into a fine powder to increase its surface area. Okay, we are good. We are good. We continue. So, yeah, so the zinc solid could be ground into fine powder to increase its surface area. So increase the surface area of a solid. If there's a solid reactant, increase attempt to increase the reaction rates. You take the solid and you decide to break it down, to grind it into, or you have it broken down into fine powder to increase its surface area. But also the HCl concentration could be increased. So because this HCl is what? Is an aqueous state. So yeah, you can just increase the concentration, or you can add a catalyst to this reaction. Okay, there are a couple of exercises. We had to look at a couple of exercises, so take it easy. Now, there are a couple of things that are very important for us to take into account, but the idea of what you call the measuring rate of reaction. Measuring rate of reaction. Measuring rate of reaction. So, measuring rate of reaction. How the average rate of reaction is measured will depend on what the reaction is, what the reactants are, and what product forms. How the average rate of reaction is measured will depend on what the reaction is, what the reactants are, and what product forms. Okay. Look back at the reactions that have been discussed so far. In this case, how was the average rate of the reaction measured? How did we measure the average rate of the reaction in our previous instances, as we have had our discussion? So the following examples will give you some ideas about other ways to measure the average rate of a reaction. Let us look at measuring the volume of gas produced per unit time. Measuring the volume of gas per unit time. Measuring the volume of gas per unit time. Okay, we continue to analyze this here. We continue to analyze this here. Okay, yeah. Measuring the volume of gas produced per unit time. How much gas is produced? Okay. Now, to understand how much gas is produced in a chemical reaction, for instance, if you have what you call the gas syringe method, you can use a gas syringe to measure the amount of gas formed, for example, or the volume of gas produced per unit time. So, like in this example, or in this experiment, the volume of gas produced in a reaction may be measured by collecting the gas in a gas syringe. Okay, you have your reactants here, and you put everything in your flask, And as more gas is produced, the plunger is pushed out and the volume of the gas in the syringe can be recorded. Very easy way. So you take the plunger. By the time you start the reaction, you make sure that the plunger is like inside, right? It's inside the syringe, right? If it's further in, this plunger, further in, you let the reaction take place, and your reactants react. The reaction goes on, and a gas is released. And now you can see, oh, this plunger is being shifted back. Okay, so as this says, the plunger is pushed out. The plunger is pushed out, and the volume of the gas in the syringe can be recorded. Then you see, you read according to the calibrations in terms of how much gas is in the syringe. You know, when this plunger is moving out, then you measure everything. You measure everything. You measure everything then. Okay, so yeah, so you continue. Okay, so we continue. By measuring the volume at set time intervals, we can graph figure 7.5 and hence determine the rate of direction. So we can measure the volume at set time intervals, and we can graph the data in that figure and hence determine the rate of the reaction. Okay, so we can decide to measure the volume, and you can see that the volume was 0 in the beginning when the plunger was like further in here, and then now the plunger starts moving back, and is pushed out. And when it is pushed out, we're able to record to say, in the beginning there was 0 volume, 0 time, and then the time started increasing in the volume was increasing when the plunger was pushed out, but also the time was increasing. As the time went, the volume also increased, and you have this kind of a graph here. So steep gradient at start of the fastest reaction. You can see a steep gradient at the start of the fastest reaction. The gradient decreases as the reaction rate slows. The gradient appears to decrease as the reaction rate slows. The gradient becomes 0, shows the reaction has stopped. That is, no more gas is. Okay, so we continue. Right, so now a plot of the volume of gas collected at set time intervals. A plot of the volume of gas collected at set time intervals. Now, the examples of reactions that produce gas as listed. Okay, we continue. We continue. Yeah. According to the volume that is pushing the plunger out, we're able to measure, sort of plot this graph here, and this is sort of used to determine the reaction rate. Okay. Examples of reactions that produce gas are listed below. Reactions that produce gas, that produce like hydrogen gas. When a metal becomes acid, like we saw a metal, like the metal was magnesium, ribbon, reacting with an acid, which is the hydrochloric acid, HCl, and a hydrogen gas is produced. The hydrogen can be collected in a test tube. A lead splint can be used to test for hydrogen. So you can take a lead splint, wooden splint, right? The pop sound shows that hydrogen is present. So there's a pop sound if you present the into the test tube that has hydrogen, that you suspect is hydrogen. So sometimes you're not sure that there's hydrogen there, but if you put your splint there, the splint is going to pop. It's going to pop, and that shows that there's hydrogen present. For example, magnesium reacts with sulfuric acid to produce magnesium sulfate and hydrogen. Okay, here's a good example of a reaction that produces reactions that produce hydrogen gas. So if you take magnesium solid and you combine with sulfuric acid in aqueous state, what you're able to get in the end is magnesium sulfate and hydrogen. Like a couple of
Sir,
yes, please.
can you please repeat? You were breaking.
Oh, okay. My apologies. Yeah, but yeah, this is recorded. In case I break, I know very well that the recording is always perfect. So yeah, but thanks for letting me know that I was breaking. The recording is always perfect in terms of sound quality. Okay, because yeah, we're recording our discussion so that you can replay this during your own time. I'm gonna send the video. Right. So examples of reactions that produce gas are listed below. Let us give examples of reactions that produce hydrogen gas. Reactions that produce hydrogen gas. When a metal reacts with an acid, hydrogen gas is produced. Okay. So what kind of metal? Now we can take here, for instance, magnesium as a solid, reacted with sulfuric acid, H2SO4, and what we're able to get is magnesium sulfate and hydrogen gas. Now, a lead splint can be used. So in other words, the hydrogen can be collected in a test tube. So you can collect the hydrogen in a test tube. A lead splint can be used to test for hydrogen. The pop sound shows that hydrogen is present. So if you suspect hydrogen is in the test tube, you present your lead splint there, and if it presents a pop sound, then you know very well that there's hydrogen present there. For example, the magnesium reacts with sulfuric acid to produce magnesium sulfate and hydrogen. Okay, so yeah, for example, magnesium reacts sulfuric acid. So you can take magnesium and put it into sulfuric acid, and then you'll get magnesium sulfate and hydrogen. So this is just an example of a reaction that produces what we call the hydrogen gas. And then there are certain reactions that produce carbon dioxide. Okay. When a carbonate reacts with an acid, like we're taking like calcium carbonate, right? And it reacts with hydrochloric acid, right? So when a carbonate reacts with an acid, carbon dioxide gas is produced. When carbon dioxide is passed through lime water, when carbon dioxide, right, very interesting, is passed through lime water, it turns the lime water milky. Okay, a burning. So if you pass carbon dioxide through lime water, you pump it into lime water, it turns the lime water milky. Okay, so the burning splint will also stop burning, be extinguished in the presence of carbon dioxide gas. Okay, these are simple tests for the presence of carbon dioxide. Okay, these are very popular in chemistry. So how do you test for carbon dioxide? To test for carbon dioxide, you pass the carbon dioxide gas through lime water. It turns the lime water milky. A burning splint will also stop burning, be extinguished in the presence of CO2 gas. These are the simple tests for the presence of carbon dioxide. So carbon dioxide will turn lime water milky. It will stop the burning of a burning splint. And if you take a burning splint of wood and you put it into a vessel that is carbon dioxide, it stops burning. And if it stops burning, it means it's carbon dioxide. Or if you think that carbon dioxide is in a test tube, then you pass it through lime water. And if you bubble that into lime water, you expose the gas, the lime water to the gas, etc. You find that these lime water turns milky. These are simple tests for the presence of carbon dioxide. For example, calcium carbonate reacts with hydrochloric acid. Calcium carbonate reacts with hydrochloric acid to produce calcium chloride, water, and carbon dioxide. So if you take calcium carbonate with hydrochloric acid, what you get is calcium chloride, water, and carbon dioxide. Okay, why are we writing this thing here? This chemical equation. This is an example of a reaction that produces carbon dioxide. Yeah, we looked at a reaction that produces hydrogen gas. This one produces carbon dioxide gas. Okay, there are certain types of reactions that produce oxygen. A reaction that produces oxygen, like hydrogen peroxide, decomposes in the presence of manganese. Right. So if you have manganese oxide, right, and oxide catalyst to produce oxygen water. Right. So now we continue as follows. We continue as follows. Okay. Okay, continue. Okay, we continue. We continue. Right. Okay, yeah, once again, in this reaction, we are looking at the fact that we are looking at directions that produce oxygen. What directions, if we want oxygen, how do you produce it? So we take hydrogen peroxide, and hydrogen peroxide decomposes in the presence of manganese oxide catalyst to produce oxygen water. So you can see that if you take hydrogen peroxide, and we can see the hydrogen peroxide, which is H2O2, it decomposes in the presence of manganese oxide, right? It's manganese oxide. These hydrogen peroxide breaks down, decomposes, right, in the presence of this manganese oxide catalyst to produce water and oxygen gas. So this is an example of a reaction that produces oxygen from hydrogen peroxide in the presence of the catalyst called manganese oxide. This one here. Okay, yeah, it is obvious now. If you want to measure the reaction rates, measuring reaction rates, in this case, for instance, the aim of this experiment becomes to measure the fact of concentration of the average rate of a reaction. Right, so I take the apparatus, which is your solid zinc granules, at 1 mole per decimeter cubed, and we have the hydrochloric acid, HCl, 2 conical flasks, 2 beakers, 2 balloons, and Bunsen burner, splint of wood. Okay, let's just continue. I don't want to spend a lot of time on those reactions. I want us to just discuss concepts. Okay, there are certain kinds of reactions that are precipitation or precipitate reactions or precipitation reactions. In reactions where a precipitate is formed, the amount of precipitate formed in a period of time can be used as a measure of the reaction rate. So the amount of precipitate formed in a period of time can be used as a measure of the reaction rate. For example, when sodium thiosulfate reacts with an acid, when sodium thiosulfate reacts with an acid, when sodium thiosulfate reacts with an acid.
With an acid.
Okay, good. Yeah, let's continue. Right, so a yellow precipitate of sulfur is formed. The reaction is as follows. Yeah, the amount of the precipitate of a period of time is used to measure the reaction rate. For instance, here is sodium thiosulfate. This one comes in the exam many times, and you'll be looking at past exam questions in a couple of minutes. All right, the reaction is as follows. All right, one way to estimate. So let's just discuss this chemical reaction a little bit. You're taking sodium thiosulfate, and we reacted with which is aqueous state, and you take HCl, hydrochloric acid, in aqueous state. What are the products? All right, you can see that the products are sodium chloride, sulfur dioxide, and water with sulfur as solid. Okay, so you take two substances in both in aqueous, and you have what you call the sodium chloride aqueous in aqueous state, sulfur dioxide, in aqueous state, water in liquid state, and also you have your sulfur as a solid. One way to estimate the average rate of this reaction is to carry out the investigation in a conical flask and to place a piece of paper with a black cross underneath. This is what possibly came in the exam. What possibly came in the exam? Yeah, I think that very similar to this came in the November exam. Exactly this one. Right, so yeah, or just a slight variation of this. When there was an X, so one way to estimate the average rate of these reactions is to carry out an investigation in a conical flask. So you take a conical flask and to place a piece of paper with a black cross underneath. So under the conical flask, you put a paper with a black cross, right underneath the bottom of the flask. At the bottom of the reaction, the cross will be clearly visible when you look into the flask. Okay, we're going to look at figure 7.6 soon. However, as the reaction progresses and more precipitate is formed, the cross will gradually become less clear and will eventually disappear altogether. Measuring the time that it takes for this to happen will give an idea of the reaction rate. Okay, well, yes, measuring the time that this takes to happen will give an idea of the reaction rate. Okay, now, the couple of things now. However, as the reaction progresses and more precipitate is formed, the cross will gradually become less clear and eventually disappear altogether. Okay, so yeah, you put the cross underneath the flask with sodium thiosulfate and hydrogen chloride gas or acid, hydrochloric acid. And now you realize, okay, the black cross under the flask is still visible, and then it will disappear. It will disappear altogether. Measuring the time that it takes for this to happen will give an idea of the reaction rate. How much time does it take from the start of the reaction to a time when you say, hang on, yeah, now I'm no longer seeing the crust underneath the flask. Note that this is not possible. Note that it is not possible to collect the sulfur dioxide gas that is produced in the reaction because it is very soluble in water. Here is this. Yeah, I saw a question like this in the November exam. So yeah, November 2023. And now, for instance, you have this. Here's an eye. Somebody's looking. You are looking into through the top of this flask, and what you are able to see through this conical flask at the beginning of the reaction when you have mixed the sodium thiosulfate and the hydrochloric acid, you really can see the cross, and then gradually it disappears. Now, at the beginning of the reaction between sodium thiosulfate and hydrochloric acid, when no precipitate has been formed, the cross at the bottom of the conical flask can be clearly seen. Okay, you can see at the beginning of the reaction between sodium thiosulfate and hydrochloric acid, when no precipitate has been formed, the cross at the bottom of the conical flask can be clearly seen. As the precipitate forms, less of it can be seen. As with precipitate, then less of it can be seen. View from the top. Without precipitate, it's very clear. With the precipitate, less of the cross can be seen. Okay, let's look at the informal experiment measuring reaction rates to measure the effect of concentration on the average rate of a reaction. Okay, right, so okay, let's just discuss this briefly. It's not very necessary want to discuss mostly the concepts here, but here's an informal experiment measuring reaction rates. And now the aim is to measure the effect of the concentration on the average rate of a reaction. The apparatus become that you take your sodium thiosulfate Na2S2O3 solution, prepare solution of sodium thiosulfate by adding 12 grams of sodium thiosulfate to 300 cubic centimeters of water. Okay, so we are preparing a solution of sodium thiosulfate by adding 12 grams of sodium thiosulfate to 300 cubic centimeters of water. You are mixing sodium thiosulfate with water. This is solution A. 300 cubic centimeters of water, 100 cubic centimeters of 1:10 dilute hydrochloric acid. Okay. So we have that. This is solution B. Right. So you add you have also hydrochloric acid. And then you have 600 cubic centimeters glass beakers. Okay, so you have 600 cubic centimeters glass beakers, measuring cylinders, paper, and marking pen, stopwatch, a timer. Okay, so yeah, you actually just doing this one. So you are just combining sodium thiosulfate with HCl, and you are having your papers. You're having your it's just an informal experiment. You want to see the cross, and you want to see the cross disappearing when HCl is mixed with sodium thiosulfate. Yeah, at some point when the precipitate forms and the cross is will ultimately disappear altogether. Yeah, I'm not going to spend a lot of time on that. Okay, let's look at the aspect of color changes. For example, in some reactions there is a change in the color, which tells us that the reaction is occurring. The faster the color change, the faster the reaction rate. So if there's a faster change in the color, that means that there's a faster reaction. For example, when ethanoic acid, which is acetic acid, is titrated with sodium hydroxide. Here's ethanoic acid is titrated with sodium hydroxide, right? Ethanoic acid is also called acetic acid, and it is titrated with sodium hydroxide. An indicator such as what you call the phenolphthalein is added. Okay, the solution is clear in an acidic solution and changes to pink when the reaction is complete. If the concentration of the base were increased, the color change would happen faster after a smaller volume of base was added, showing that a higher concentration of base increased the reaction rate. Okay, so yeah, for example, ethanoic acid, which is acetic acid, is titrated with so you take an acid which is a weak acid. Acetic acid is a weak acid. It's mostly of vinegar. It's mostly termed vinegar in the household. And now you combine the acid, so it's a titration reaction where you actually add the acid a little bit to the base, and you keep shaking the flask. So for example, when the ethanoic acid, acetic acid titrated with sodium hydroxide, an indicator such as phenolphthalein is added, right? The solution is clear in an acidic solution and changes to pink when the reaction is complete. Yeah. So the solution is clear in acidic solution and changes to pink when the reaction is complete. There. So you're mixing an acid with a base. Now, if the concentration of the base were increased, the color change would happen faster after a smaller volume of base was added, showing that a higher concentration of base increased the reaction rate. So now, if you have here the following. So you have ethanoic acid, which is an aqueous state. Right, ethanoic acid with sodium hydroxide base. And now you have the ionic substances that are formed, which is your sodium ion, your ethanoate ion, and your water. Both the sodium ion is in aqueous state, and the ethanoate ion is in aqueous state, and water is the liquid. Okay, the color changes here, and we can see the color change is to do with the phenolphthalein indicator. And this phenolphthalein indicator, once again, we said that the solution is clear in an acidic solution, right? And it changes to pink when the reaction is complete. Obviously, we understand that this is about pH, and we understand that in a titration reaction, when you're mixing a base with an acid, then ultimately we get a neutral solution in the end. But it is clear, in other words, phenolphthalein is clear in acidic solution, but it is pink in when the reaction is complete. So this we attempt to achieve a neutral solution. Now there's change in mass. change in mass during a chemical reaction. So one way to study chemical reactions is to change in mass. For a reaction that produce carbon dioxide or that produce gas. Okay, right. So let's just look at change in mass. For a reaction that produce gas, the mass of the reaction vessel can be measured over time. The mass loss indicates the amount of gas has been produced and escaped from the reaction vessel. So if there is a change in mass, then those reactions, the mass loss indicates the amount of gas that has been produced and escaped from the reaction vessel. Change in mass. So we continue. Okay. If the reaction vessel is sealed, this method will not work. Yeah, because there's a gas, it has to be sealed. Right. If the reaction vessel is sealed, this method will not work. Okay, yeah, if it's sealed, then I mean the gas escapes and it will leave. So we expect that the mass is going to reduce because the gas will be leaving. But if you seal it, then the gas is not going to be able to escape. So cotton wool allows gas to escape, not liquid. So yeah, cotton wool, if you put it there, it allows the gas to escape, but not liquid. So yeah, we're good. We're good. We're good. So we continue. Figure 7.7, a change in mass indicating the loss of gas. Okay, so now when the gas is lost, so you can see that, okay, the mass is decreasing, and appears to be constant over time. So yeah, that is when there is loss of mass. So notice the difference between the two graphs in figure 7.8. The mass of the sample will decrease as the reaction proceeds. So the mass of the reaction, the mass of the sample will decrease as the reaction proceeds. The mass lost from the sample will increase as the reaction proceeds. Yeah, the mass you are losing is going to increase. The mass loss is going to increase. As the reaction proceeds, the material loss that accounts for the mass loss, it can be collected and measured. For example, with mass, with the gas syringe method is shown. Right. So yeah, we're saying the material loss can be collected and measured. For example, with the gas syringe as shown in figure 7.4. Right. So yeah, we can see, yeah, we saw that we can use the gas syringe. We saw that we can use the gas syringe to measure the material lost and the gas lost. So the mass lost increases, but we understand that the mass of the sample will decrease and the mass loss will increase over time. Okay. So we continue. The graph of the sample mass versus time, and B, the graph of the mass loss versus time. Mechanism of reaction and catalysis. Mechanism of reaction versus and catalysis. Right, earlier it was mentioned that it is the collision of particles that causes the reactions to occur, and that only some of these collisions are successful because some of the collisions are not successful. This is because the reactant particles have a wide range of kinetic energies, and only a small fraction of the particles will have enough energy. Only a small fraction of particles will have enough energy and the correct orientation to actually break bonds so that the chemical reaction can take place. The minimum energy that is needed for a reaction to take place is called the activation energy. The minimum energy that is needed for a reaction to take place is called the activation energy. Okay, yeah, activation energy is the minimum energy that is needed for a reaction to take place. For more information on the reactions, this is done in grade 11. Okay, let's discuss activation energy, etc. For its definition, activation energy, the minimum energy required for a chemical reaction to proceed. The minimum energy required for a chemical reaction to proceed is called the activation energy. Right, even at a fixed temperature, the energy of particles varies, meaning that only some of them will have enough energy to be part of a chemical reaction, depending on the activation energy of that reaction. Increasing the reaction temperature has the effect of increasing the number of particles with enough energy. So if you increase the temperature, this has the effect of increasing the number of particles with enough energy to take part in the reaction and increasing the reaction rate. Okay. So probability of particle with that kinetic energy. Probability of particle with that kinetic energy. So now let's look at activation energy. The proportion of particles with sufficient energy to react. So the kinetic energy of particle, for example, here's the kinetic energy of particle. Okay, the activation energy here, which is the minimum energy, and this is the energy axis. And we can see that this is certainly minimum energy, which is required for a reaction to take place. So distribution of the particle kinetic energies at a fixed temperature. Okay, this is at a fixed temperature. We're showing distribution of kinetic energies at a fixed temperature. And we're building our momentum towards what we call the Boltzmann constant before we look at past exam questions. Remember that a molecule must have energy greater than activation energy as well as correct orientation for the reaction to take place. Remember that a molecule must have energy that is greater than activation energy as well as the correct orientation for the reaction to take place. So yeah, this one is at a fixed temperature. This is the curve at a fixed temperature. Probability of a particle with that kinetic energy, the kinetic energy of particle there. Okay, proportion of particles with sufficient energy to react. Okay, so you'll have the reaction effectively taking place at energies greater than the activation energy there. Okay, let us look at what happens next. So what happens when we are increasing the temperature of a reaction mixture? So increasing the temperature of a reaction mixture raises the kinetic energy of the particles. Increasing the temperature of a reaction mixture raises the average kinetic energy of the particles. Okay, so if you increase the temperature of a reaction mixture, what does the increase in temperature do? All right, so it raises the average kinetic energy of the particles. So if you heat the reaction mixture, the average kinetic energy of the particles also increases, as can be seen on the graph in figure 7.10. A higher proportion of the particles can now react, making the reaction faster. With the increased movement of the molecules, the chances of a molecule having the correct orientation is also increased. Okay, now let's look at what happens in the Boltzmann. Discuss this very briefly, but we have a fair chance to discuss it today. Right, at lower temperature, you'll have the peak that is a little bit higher, and you really can see that the peak is a bit less at higher temperature. This is counterintuitive because at higher temperature, the peak is less, and at lower temperature, it is much higher. Now, the proportion of the particles with sufficient energy to react is obviously and can actually be seen there. But what you're able to see is a couple of things here that remain very, very important. So increasing the temperature of a reaction mixture raises the average kinetic energy of the particles. If you heat them, then they start roaming around. If you heat them, they gain a lot of average kinetic energy. And as can be seen in the figure 7.10, a higher proportion of the particles can now react, making the reaction faster. So yeah, if you heat the reaction vessel, kinetic energy, these guys, they start the gas molecules, gain a lot of average kinetic energy, and they start increasing the rate of the reaction. With the increased movement of the molecules, the chances of a molecule having the correct orientation is also increased. With the increased movement of the molecules, the chances of a molecule having the correct orientation is also increased. Yes. Okay. Higher temperature, the peak is a bit less. So the graph sort of flattens. The proportion of particles with sufficient kinetic energy to react. But you can see the proportion of particles with sufficient kinetic energy to react, the proportion increases, okay? Because there are those particles where this was the initial green curve, and now you can see the proportion increases. Proportion of particles with sufficient kinetic energy increases with the increase in temperature. Okay, this is awesome, awesome, awesome news. The distribution of particle kinetic energies with increase in temperature. When increased temperature, there's a distribution of the particle kinetic energies. Right there, there is an increase. Right, there's an increased number of particles with sufficient energy due to higher temperature. There's an increased number of particles with sufficient energy due to higher temperature. Due to higher temperature, there's an increased number of particles with sufficient kinetic energy. Okay, there with sufficient kinetic energy, there's an increased number of particles there. Okay, now let's look at the idea of what we call the endothermic reaction can be represented below. Okay, now if the reactants gain energy in an endothermic reaction, so it's a kind of reaction. We saw that the reaction that absorbs energy is called endothermic. So if you take reactants and you add energy in the form of heat or increase in temperature, the products are formed. This can be shown in an activation energy diagram, which is 7.11. These graphs are also sometimes called a reaction profile or a potential energy graph. Okay. Okay, now if you look at potential energy, that increases, the time increases. And now if you look at the reactants are there and the products also are most certainly there. This can be shown. These can be shown in activation energy diagram 7.11. These graphs are sometimes called the reaction profile or potential energy graph. We call these reaction profile or potential energy graph. Okay, when you can see there's activation energy and the activated complex is labeled, the products are here, the reactants are there, there's activation energy, and you have the energy that is added because we're saying reactants plus energy, and if you take reactants and you add energy in the form of increased temperature, the products will be certainly formed there. Now, these activation energy diagram, we call these the activation energy diagram, or you can call it the reaction profile or a potential energy graph. Potential energy is on the vertical axis and time on the horizontal axis. Now, the activation energy diagram with reactant energy lower than product energy is that is endothermic. Endothermic. So, in other words, the activation energy diagram with reactant energy, so the reactant energy lower than product energy is called endothermic. So this is endothermic because the reactant energy is lower than product energy. The reactant energy is at this level, but the product energy is higher here, and you can see it here. It's actually called endothermic reaction there. Okay, there's an exothermic reaction that can be shown below and can be represented by the following. So if you, for instance, the reactants now, if they happen to break down and give products plus energy, that is energy that, a reaction that releases energy. Right, there's a reaction that releases energy. Okay. This can be shown in an activation energy diagram. This can be shown in an activation energy diagram. This can be shown in an activation energy diagram. Okay, right, let's continue. There's potential energy here, but you can see that the reactant energy, the activation energy diagram with reactant energy greater than product energy is called exothermic reactions. You can see that the products themselves, the reactants produce products and energy. So yeah, reaction that releases energy is called exothermic. It can be shown here. So we have potential energy. So these are the length in the graphs length in grade 11. So yeah, the tip is that the activated complex occurs. An activated complex occurs in reactions without catalysts as well as those with catalysts. Okay. Okay, we are looking at the notion of what we call an endothermic reaction, and in an endothermic reaction, you can see the potential energy on the vertical axis in the time there. But now, if the activation energy diagram with the reactant energy is greater, and you can see the products have less energy. The product energy is less. So this is called an rather an exothermic reaction. It's called an exothermic reaction. Okay, so okay, this is seen in grade 11 mostly. Okay, it's grade 11 work. So how do catalysts work? Let's have a catalyst increases reaction rates in a slightly different way from other methods of increasing reaction rate. So yeah, a catalyst increases reaction rate. The function of a catalyst is to lower the activation energy so that a greater proportion of particles have enough energy to react. A catalyst can lower the activation energy for a reaction by, so how does it do that? By orienting the reacting particles in such a way that successful conditions are more likely. Reacting the reactants to form intermediate that requires lower energy to form the product. So some metals, e.g. platinum, copper, and iron, can act as catalysts in certain reactions. Right, so in our own bodies, we have enzymes that are catalysts which help to speed up biological reactions. Catalysts generally react with one or more of the reactants to form a chemical intermediate. Okay, which then reacts to form the final product. The chemical intermediate is sometimes called the activated complex. The activated complex. The following, for instance, is an example of how a reaction involving a catalyst might proceed. A and B are reactants, and C is a catalyst. So if A is a reactant, and we're saying A and B are reactants, and C is a catalyst, C is a product of the reaction of A and B. We continue. In step 1, we react this reactant A with a catalyst, and then we form a product. This is just a general chemical reaction. Reactant B also, and now it reacts with, now we got the AC, and then now AC reacts with B to form ACB, and ACB now breaks down to, in the end, you have the catalyst formed and you have the product D. So the catalyst itself, in the end, is released and without any chemical change. So ACB, which is this one here, represents the intermediate chemical. Although the catalyst C is consumed by reaction 1, it is consumed by reaction 1, it is later released again by reaction 3, so that the overall reaction with the catalyst is as follows. Yeah, so that the overall reaction becomes that you add A plus B plus C. What you're getting, the catalyst is just going to be there. There's going to be a product there, but the catalyst is going to be released as it was added in the beginning. You can see from these that the catalyst is released at the end of the reaction completely unchanged. Catalyst is there, unchanged, nothing, nada. Okay. Without a catalyst, the overall reaction would be, without a catalyst, you would just be combining reactant A plus reactant B to get the product D. Just look at this particular interesting graph that comes in the exam. Right, the catalyst has provided an alternative set of reaction steps. The catalyst has provided an alternative set of reaction steps, which we refer to as an alternative pathway. Okay, so the catalyst is providing an alternative set of reaction steps. which we refer to as an alternative pathway. The pathway involving the catalyst requires less activation energy and is therefore faster. This can be seen in the following diagram. Okay, let's look at the probability of particle with that kinetic energy. Kinetic energy of particle Ke. Okay, we continue. Okay, let's look at kinetic energy of particle Ke, for example. Now, there's something called the activation energy. And with the okay, let's look at this. With the catalyst, the activation energy is reduced. So the catalyst lowers the activation energy without taking part in the reaction. And the original activation energy was here, but with activation energy with the catalyst now it's less. So figure 7.13, the proportion of particles that have enough energy to react is increased in the presence of a catalyst. The proportion of particles with that have enough energy to react is increased in the presence of a catalyst. Okay, in the presence of a catalyst, what we're able to see is that the proportion of particles that have enough energy to react is increased in the presence of a catalyst. Okay, the catalyst, what it does, right? So it increases the proportion of particles that have enough energy to react. If you add a catalyst, there is an increase in the proportion of particles that have enough energy to react, and thereby lowering the activation energy there. Okay. Okay. Let's look at a very good definition. What is a catalyst? What is a catalyst? A catalyst speeds up a chemical reaction without being consumed by the reaction. It increases the reaction rate by lowering the activation energy for a reaction. We repeat, catalyst. So a catalyst speeds up a chemical reaction without being consumed by the reaction. It increases the reaction rate by lowering the activation energy for a reaction. Energy diagrams are useful to illustrate the effect of catalyst on reaction rates. Catalysts decrease the activation energy required for a reaction to proceed. Okay. Catalysts, what do catalysts do? They decrease the activation energy required for a reaction to proceed. Yeah, so anyway, the activation energy has changed, so it's decreased. Right, the activation energy required for a reaction to proceed, and therefore the increase in the reaction rate, and therefore increase the reaction rate. Remember that with the catalyst, the average kinetic energy of the molecules remains the same, but the required energy decreases. Okay, this is very important. Remember that with the catalyst, the average kinetic energy of the molecules remains the same, but the required energy decreases. Okay, we're back to grade 11. Potential energy versus time. The reactant energy is and you have this one obviously there, which we can see therefore that the reactant energy is less. So the effect of a catalyst on the activation energy of an endothermic reaction, the catalyst would act in the same way for an exothermic reaction. Okay, let's look at this one where you have the activation energy with the catalyst. So the activation energy of the catalyst is reduced. The activation energy of the catalyst is reduced, but the activated complex is higher. The activation energy can be seen here. The reactants can be seen. The reactant energy is at this level, and the product energy is much higher when the reactant energy is much lower. Right, so the effect of the catalyst on the activation energy of an endothermic reaction. The catalyst would act in the same way as for an endothermic reaction. So you can see that the catalyst decreased the activation energy. Okay, so yeah. So the activation energy for the activated complex, which was originally there, the activation energy with the catalyst is now decreased, smaller. Right, the catalyst would act the same way for an exothermic reaction. Okay, we continue and we analyze this. I want us to go to past exam questions. Okay, so you have the chapter summary, etc., 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 and I want us to discuss briefly the summary. Okay, let's discuss briefly the summary of the chapter. Right, so now the summary of this chapter on the rate and extent of reaction. The average rate of reaction describes how quickly reactants are used or how quickly products form. The units used are usually moles per second. So yeah, the number of factors can affect the a number of factors can affect the average rate of reaction. This includes nature of the reactants, the concentration of solutions, surface area of solids, or pressure of gases, the temperature of the reaction, and the presence absence of a catalyst. Okay, I want us to look at this point. Very strong point, but very important. A number of factors that can affect the average rate of a reaction. What are these factors? The factors are, these include the nature of the reactants, the concentration of solutions, the surface area of solids, the pressure of gases, the temperature of the reaction, and the presence or absence of the catalyst. So you have 1, 2, 3, 4, 5, 6. We have discussed about 6 different factors that affect the average reaction rate. Collision theory provides one way of explaining why each of the factors mentioned in the previous bullet can affect the average rate of a reaction. Okay. Collision theory provides one way of explaining why each of the factors mentioned in the previous bullet can affect the average rate of a reaction. For example, higher temperatures mean increased reaction rates because the reactant particles move, or rather have more energy and are more likely to collide successfully with each other. Okay, let's just look at the different methods can be used to measure average rate of a reaction. The method used depend on the nature of the product or products. Reactions that produce gases can be measured by collecting gas in a syringe or by measuring a change in mass of the reaction vessel. In reactions that produce a precipitate, the mass of the dried precipitate can be measured. Okay. Change in color can show the product has formed or that the reaction has reached completion. Change in color can show that the product has formed or that reaction has reached completion. We saw that in the case of the sodium thiosulfate and the black cross at the bottom of the flask. Okay, for any reaction to occur, there's something that we take into account. Okay, for any reaction to occur, a minimum amount of energy is needed so that bonds in the reactants can break and new bonds can form in the products. The minimum energy that is required is called the activation energy of a reaction. So you need, for a reaction to occur, you need what you call a minimum amount of energy, and that is called the activation energy. And this activation energy, what does it do? So that the bonds in the reactants can break and new bonds can form in the products. Okay. Okay, we'll continue. In reactions where the particles do not have enough energy to overcome this activation energy, one of 2 methods can be used to facilitate a reaction to take place. Increase the temperature of the reaction or add a catalyst, okay? So sometimes in reactions where the particles do not have enough energy to overcome this activation energy, there are some reactions with less activation energy, but very small activation energy. So what then happens there, if the reaction is not happening, is not taking place, we have the we have the reactants there, but nothing is happening. One of two methods can be used to facilitate a reaction to take place. You increase the temperature of the reaction, or you add a catalyst. Let us look at increasing temperature of a reaction. Right, increasing the temperature of a reaction means that the average energy of the reactant particles increases as they become, they're more likely to have enough energy to overcome the activation energy, and the chances of two molecules having the correct orientation are increased. Let's repeat that one. Increasing the temperature of a reaction means that the average energy of the reactant particles increases, and they are more likely to have enough energy to overcome the activation energy, and the chances of two molecules having correct orientation are increased. Right, a catalyst is used to lower the activation energy so that the energy is more likely to take place, so that the reaction is more likely to take place. So now the catalyst is used to lower, so that in the Boltzmann's curve, that the catalyst is used to lower the activation energy so that the reaction is more likely to take place. Catalyst does this by providing an alternative lower energy pathway for the reaction. Lower energy pathway is an alternative lower energy pathway for the reaction. Right, so a catalyst therefore speeds up a reaction but remains unchanged after the reaction is complete. Okay. We continue. Catalyst therefore speeds up a reaction but remains unchanged after the reaction is complete. Okay. Catalyst speeds up a reaction but remains unchanged after the reaction is complete. Okay, we shall look at a couple of exercises. We shall look at a
Are you
couple
doing
of...
questions now?
Please come again. Yes, we're doing
Are we
questions.
doing them now?
Yes.
Mm.
I was thinking that we do past exam questions. Okay, I was thinking that we do past exam questions. Okay, let's just look at this question that was set in the in one of the past exam questions. And now we're looking at this is question 5 in one of the past exams. Let us spend some time to discuss these together, but very, very quickly. Right, we started at exactly 8 a.m. and I'm expecting that we're gonna finish at approximately 10. Okay, we shall
10
yeah. What do you think?
is 10
It's almost 10 now, right?
is
Yes. Do you still have the energy? Yes? Or you're a bit exhausted
no
already?
is
You're tired. So, okay.
we can do the questions next week.
Okay, that's fine. We'll do the questions next week. Okay, thank you so much. That's okay. Right, so yeah, these are the questions that we're going to discuss next week in terms of how we use the theory to solve past exam questions. And obviously, I mean, you're right, the time would mean that I would have to like run really fast through these questions. But these are very important. But not only that, but yeah, we will give you, I'll give you more practice problems, you know, next meeting next week on the rates of reactions. Right, so right, it was awesome having this discussion then, because we can see that we are just 6 minutes, 6 minutes away from the end of this discussion. You see how many minutes are we left with? You see, according to my time, is 6 minutes, right? Right. Anyway, yeah. Let me not crack your skull and make you. Yeah, you need to digest, because I'm gonna send you the video that we have made. So, okay, in this question that we're going to discuss next week, it is about the reaction between zinc and hydrochloric acid. Okay, zinc split in hydrochloric acid. But what we can see is, after this is one reaction that is able to produce what you call hydrogen gas, and we saw that we can be able to test for hydrogen for instance, using a glowing split. Okay, so we're going to discuss questions like this. Define reaction rate. We've defined that, but we're going to define that. And we're going to look at how we can write down the value of X. And we're going to look at a couple of experiments. We're going to look at the Maxwell-Boltzmann. And we're going to look at the experiment 6. Okay, there are different types of experiments there. And we're going to calculate for 4 marks the average rate of the reaction in moles per in moles per minute with respect to zinc for experiment 2 if 1.5 grams of zinc is used. Okay, yeah, it was really awesome having this discussion this morning, and we shall continue and make sure that in the end it all goes well and we understand how to answer but a lot of questions on rates of reactions. Right, we've had a chance to discuss this, but yeah, there are more things that, more questions we're going to look at next week. Not only obviously this particular question, but like tons and tons of other questions on reaction rates to make sure that students are assisted and students can understand what is happening very, very well. Right, so yeah. So I think therefore we had a fair part of our discussion. And obviously I'm thinking of what next. Okay, yeah, we shall spend a reasonable amount of time on these questions here to ensure that everything is most certainly very, very well understood. And we're able to, okay, in particular, and this question that, this one, which is zinc solid plus hydrochloric acid, okay, is the same as zinc sulfide plus hydrochloric acid that we looked at as in our example 2, because in our example 2, we wrote a balanced equation for the exothermic reaction between zinc solid and hydrochloric acid, and also we had to name 3 ways to increase the rate of this reaction. Okay, yeah, zinc and hydrochloric acid, we wrote the balanced equation, and we also looked at the 3 ways to increase the rate of this reaction. And the examiner brought the same thing here. Brought the same thing, zinc and hydrochloric acid, and different ways to increase the rate of the reaction. But yeah, it's very interesting this, because now first step was to write down the equation for zinc and hydrochloric acid. How to write down? We said if you actually react zinc with HCl, what we then have is that, okay, zinc, okay, the products must be salt and hydrogen gas, because we are reacting a metal with an acid. So if you react a metal in solid with an acid, you get hydrogen gas and a salt. So in other words, zinc ions have a charge of 2 plus. So zinc has a charge of 2 plus, while chloride ions have a charge of 1 minus. Therefore, the salt must be zinc chloride. This is the salt, and hydrogen gas is obviously produced. Okay, we saw that it was not balanced. I'm just recapping on that. We saw that it was not balanced, and to balance it, we realized that here with Cl2, and realized that we have actually 2 chlorine or chloride ions, and we realized that we have 2 hydrogen atoms here, and we needed to put a 2 there so that we have 2 hydrogen atoms, and Cl2, and because here it's only 1 Cl, so that we have 2 chloride ions. So we put a 2 there, and we put a 2, and we put a 2 here. We have H2 and 2 hydrogen hydrogen atoms on the left and 2 hydrogen atoms on the right. And yeah, how would you increase this? So yeah, to increase the think about methods mentioned in the section that would increase the reaction rate. Okay, how can we make sure that this reaction rate is faster? We looked at the fact that we're dealing with a solid, we're dealing with an aqueous state, HCl, hydrochloric acid. So a catalyst can be added. So you can add a catalyst to this. Okay, if we don't want to add a catalyst because this one is a solid, we can take this zinc, which is a solid, and this could be ground into a fine powder to increase its surface area. We can increase surface area of zinc, or we can take the HCl concentration, and this HCl concentration could be increased. So we can increase the concentration of the HCl. So these are some of the 3 ways you can use to actually increase the rate of the reaction. It was awesome having a discussion with you there. Never, right, we keep in touch. Obviously, I'll do a lot of exam questions on rate of reactions in our next meeting next week. Yeah, thanks a lot then, and yeah, have a good morning. I'll keep you posted with more questions. Okay,
Okay.
thanks, Neo, and goodbye, Neo.
Bye.
Goodbye,
Bye.
goodbye, Neo.